Hello there, my name is Christopher Rennison and my final year project is titled GPU-based simulations of magnetic skyrmion logic gates. In this screencast I'll be explaining what that means and I'll be demonstrating what I've achieved. So to start with, Boolean logic and by extension Boolean logic gates are fundamental to modern computing. Virtually all digital computers today use Boolean logical algorithms. Traditionally, the logic gates are made from transistors. However, recently there's been motivation to study the feasibility of skyrmion-based logic systems due to their potentially low power characteristics that may open new or complementary application areas and offer a greener alternative for the environment. So, what is a magnetic skyrmion? Well, to use a visual metaphor, if you were to imagine when water flows down a drain, it creates a vortex. A skyrmion is like a vortex but within a magnetic field. These skyrmions are relatively stable, non-volatile structures that in experimentation have been used as Boolean information carriers. When an electric current is applied to a metal wire with a skyrmion on it, the skyrmion will move relative to that current, which can be exploited to create the complex structures such as logic gates. While previous research has simulated a skyrmion-based logic gate, this was done assuming the temperature to be absolute zero. This project has gone beyond current research by taking the challenging, time-consuming task of simulating room temperature logic gates. This is a fundamental step towards realizing these devices. Room temperature simulations are challenging as the extra energy causes instability and variation in the skyrmion velocity, which affects timing control, and counteracting this energy requires modifications in the metal structure. The simulations themselves also run much slower, which reduces the number of possible experimentations. The logic gates that I've created in this project are the AND/OR gate and the not copy gate. This creates a universal set of logic gates that can be used to recreate any Boolean algorithm with a skyrmion-based system, and this by extension means that they can implement current processor designs and most importantly, existing code. The truth tables that you can see here represent the expected output given each input combination for both gates. These gates are unusual as they combine traditionally separate logical functions into a single gate, for example with the and OR gates into a single AND/OR gate. This is a byproduct of creating a logic gate which preserves the total number of skyrmions in the system, i.e. where no skyrmions are created or destroyed. It has been decided to use this method of conservation because it reduces the power consumption of the gates. The first gate that I simulated was the absolute zero AND/OR gate from the skyrmion logic system for large-scale reversible computation research paper. This was done as the project required a high-level understanding of complex magnetic physics, therefore the current research doubled as an opportunity to gain that understanding and could be used as a benchmark for comparison against the room temperature logic gates. Here is the result of those simulations, which by the way were simulated using the GPU accelerated micromagnetic simulation software NUMAX 3. You can see how the skyrmions are travelling through the gate in each of the different input combinations to arrive at the correct output. Due to the in-plane current, the skyrmions travel vertically upwards, and they also have a horizontal force pushing them to the left. So in the 1-0 case, the left skyrmion travels straight. In the 0-1 case, the right skyrmion travels left through the gap into the left channel, and in the 1-1 case, they repel each other at the crossing to stay in their original channels. Here is the same AND/OR logic gate, but this time simulated at room temperature. You will immediately notice that the tracks are bigger, the skyrmions are larger, and the presence of synchronization triangular notches. Synchronization is integral to digital electronics. It ensures that the operations occur in lockstep to each other, which creates known states in the design. This accounts for timing variation, and is also useful for design validation. Here it has been used to guarantee that the skyrmions meet at the central crossing at the same time in order to repel each other. As mentioned earlier, temperature adds variation to the velocity of skyrmions, so the synchronization helps reduce this effect by minimizing the distance before the crossing. The skyrmions cannot pass the crossing until a large pulse of current gives them the energy needed to overcome it. I have tried to demonstrate this pulse with the graph on the right. Also notice, the time of the simulation is longer than before in this absolute zero design due to the temperature mitigation, larger track geometry, and the synchronization delay. This is the not copy gate, also at room temperature. It uses the same principles as before and is essentially an extension to the previous AND/OR gate, although it does differ slightly as it always requires an input skyrmion in the right channel to act as a control signal. This is because a standard NOT gate outputs a 1 when the input is 0, but our gates must output the same number of skyrmions as inputted. So in the input 0 case, this control skyrmion moves into the central channel to create the output 1. And in the input 1 case, the control skyrmion is repulsed at the first crossing and remains at the right channel, while the data skyrmion moves into the left. This is the copy part of the gate, And in standard computing, this is normally known as a fan-out function, which is important for signal duplication and distribution. Another way the not copy gate slightly differs from the AND OR gate is that it requires a second current pulse for the skyrmions to fully pass through to the end. This is because they grow too large to squeeze themselves back into the channel. However, despite the second pulse, the gate is still compatible with the AND OR gate. Unfortunately, due to time constraints, I was unable to simulate more complex structures. But to demonstrate that capability, here is an example of a possible implementation of a combination of the AND OR gate and the not copy gate into a single NOR gate, a gate with the universal property I mentioned earlier. And as a quick summary of my achievements so far, I have replicated the same logic gate functionality of current research. I have taken this a step further and took on the challenging task of implementing room temperature logic gates and succeeded in making them functional, which goes beyond current research. I have also implemented a synchronization method at room temperature and proposed how to create more complex logic structures. During the wait for the long simulations, as an extension to my project, I investigated creating novel 3D visualizations of the data. In the end, I created a generalized script to create these professional visualizations for the use of other members of the micromagnetic community. It works by loading the simulation data into the open source 3D computer graphics software Blender, a powerful versatile tool that incorporates realistic lighting and modeling, and is used in a wide range of applications such as games, films, or video editing. What you can see here is an example of one of those visualizations that I have made in the room temperature and or gate. I am now going to demonstrate a quick overview of using the script. Firstly, open the software tool and navigate to the scripts tab at the top. Then after clicking open, a file browser will appear where you can select the script, and if it has the right settings, click run script. This will load the simulation data into the tool and can take a few minutes depending on the number of cones being created. Afterwards, navigate back to the layout tab, and here you can see the simulation has been loaded. Now, you can play around with the lighting, the camera settings, and any other effects you may want to add. The quality of the final product will massively vary depending on the steps you take here, but I had no prior experience with the tool or visual effects, and even I was able to create something that looked good, so you'll be able to as well. When you're ready, navigate to the rendering tab and click render for the result. This could take a while depending on the capabilities of your system. My mid-range graphic card took about 30 minutes to render a 30-second clip. Here is another example of one of the visualizations that I created using this process, this time with the absolute zero and or gate. This one looks smoother because it does not have any noise variations caused by temperature. As I mentioned, I hope that this workflow can be used and expanded by others in the field to create their own visualizations. Thank you for watching.